Okay, I'm going to share my screen. Um, can you all see the first page of my PowerPoint? Patricia, can you see that?
Yes.
Cool, thank you. So thanks to everyone for joining the session. My name is Zahra Zulfaghari. I'm the research team lead here at Cove.tool, and I have a background in architecture and building science. I will be hosting today's webinar with the topic of building performance analysis and optimization for K-12 projects. Here is the more detailed agenda for the call. We'll first go through some key considerations and sustainability trends when it comes to school design. And then I will show a school case study which was analyzed and energy optimized by using cove.tool. Then some key takeaways at the end of the call. And I also try to save 2 to 3 minutes for some questions and answers. But since we have a lot of attendees today, we may not be able to cover all of your questions at the end of the call. So please drop your questions in the Q&A section as I'm presenting. And my colleague Patricia, who is also on the call, will answer your questions during the presentation. With that, let's get started. I like to start with mentioning why it is important to design sustainable schools. The reason might be obvious for some, but believe it or not, it's not obvious for many. There are three major reasons why sustainable school design is so important. First is unhealthy learning environments. Every day, 25% of Americans go to school as teachers, students, staff, or administrators. The Environmental Protection Agency, or EPA, states that half of this population is exposed to polluted indoor air, chemical fumes, mold, and other toxins. On top of daily exposure, the amount of time students and teachers spend indoors is significantly higher in the US than in other countries. One study found that a typical US student spends about 8,800 hours over 9 years to complete primary and lower secondary school, while teachers also spend about 2,000 hours indoors working each year. So if students and teachers are going to spend the majority of their time indoors, healthy indoor air quality is absolutely essential. The second reason is climate change. With the effects of climate change inspiring more eco-friendly practices around the world, sustainable school design is one way for school districts to make a positive impact and set an example for their students and also help them becoming more environmentally friendly, more environmentally cautious citizens in the future. And then the third reason is significant operation and maintenance cost saving. In addition to reducing their carbon footprint, schools can also significantly lower operating and maintenance costs by implementing environmentally friendly practices, sustainable practices. With that quick intro, um, let's see what are the sustainability trends in school design these days. A growing trend in K-12 schools is to make the energy efficient systems in a building more visible, so they may be used as a learning tool. These sustainable features may include green roofs, rainwater collection for reuse, solar PV, solar panels, or special facade shading systems. While these systems may be complicated in how they are integrated into a building or how they operate, the school facilities will create simplified explanations for the systems related to how these systems create the overall learning environment for the building occupants. Designing to make these sustainable features visible, cost effective, and easy to understand sometimes results in a set of conflicting goals that must be balanced by the design and construction team to educate the designers and builders of tomorrow. The other good trend is daylighting in view. Through daylighting, electric lights are dimmed or turned off when there's enough natural light. Also, if coupled with very efficient lighting systems like LED or compact fluorescent lights with higher efficacy, we can see a significant lighting load reduction from the building. Since lighting accounts for about 1/3 of the electricity used by schools in the US, Daylighting saves on energy and cost. So this is an example of how the environment and school budgets both can benefit from this decision. But apart from the energy and cost benefits, studies showed that natural light and also ample view to the outside are important for students' mental and physical health. So these two factors can be very impactful to design a good sustainable school. The next important thing is indoor air quality. Poor indoor air quality can cause respiratory issues that make it hard for anyone to perform at their best, whether it's a 6-year-old student or a 45-year-old counselor. Schools can make learning environments more comfortable and less detrimental to the health of occupants by paying attention to the quality of the indoor spaces. Air quality of indoor spaces. Every school may have a different approach since different areas of the country experience their own unique weather and climate patterns. But overall, the EPA advises several strategies like using materials with low volatile organic compounds or VOCs and other toxins, installing properly designed HVAC systems that controls temperature, humidity, changing filters regularly, and incorporating outdoor air for ventilation, and also removing odors and pollutants through pressure control or filtration and exhaust fans. Uh, in addition to the right HVAC system and ventilation, using the right operational control systems and accurate occupancy schedules is also very important in reducing the school's energy consumption. The next is materials and products. Materials and products that goes into a building is another factor. Building with non-toxic materials can be healthier for people, while sustainably sourced materials reduce waste and lower energy consumption during the manufacturing process. Thus, there will be less embodied energy and embodied carbon associated with these products. Uh, Recycled, reclaimed, and locally sourced materials, as well as rapidly renewable materials like bamboo or cork, are just a few of the many options available. Just remember that new sustainable products are developed every year, so your options can increase and you will have like a wide range of options to use. Next is water and plumbing. So efficient plumbing systems and fixtures with lower water consumption is another strategy to reduce water use and therefore energy use in buildings. Energy actually is used to process and transfer water. So reducing water consumption definitely helps with reducing the energy consumption. And finally, using renewable energy. Photovoltaic panels or grid credits is another effective way to offset some energy from the buildings. With that, let's see how we can use cove.tool to assess the impact of these strategies and come up with the best decisions in the design process. Here are the 4 main features I used in cove.tool to put together this presentation. This project is one of the old projects related to the time when cove.tool was still a sustainability consulting firm and not a software company yet. I took the model and ran it through cove.tool this time to show how you can start in cove.tool and optimize a school project. So for those of you who are not familiar, the first step was to set up a project in the tool. Setting up a project is easy in cove.tool. You just need to enter your project name, its location, its address, use type, and measurement unit. Energy code will be selected based on your location, but you have this option to change it if you want to continue with more or less stringent codes. We have about 14 different energy codes in our code library. Not all of them are listed in the dropdown, but when you enter the right location, the right energy code will pop up. For example, if you have a project in California, when you enter California as your address, Title 24 will pop up, or same thing for international location. So if you like to see what energy codes are available in cove.tool, you can just click on this question mark, and you will be directed to a help article where you can see the list of all the energy codes. Based on this energy codes and other selections in this page, like the building type and your location, all the code minimum inputs necessary for energy simulations and other types of analysis will be automatically populated for your project. Therefore, even if you are in an early design phase and don't have all the information and details about your project, you can still get a baseline energy consumption, which is based on minimum standards, and you can use that number actually for benchmarking and setting up target for your projects, energy targets, and also carbon targets. After setting up the project, we took a look at these climate diagrams, which are listed on the climate analysis page. To understand the climate and its potentials, this early observations really help with massing and orientation decisions, landscape design, and the amount of free running or unconditioned outdoor spaces in the design. It also gave us a glimpse of what should be the main point of consideration when it comes to design process. For example, by looking at the relative humidity diagram, you can tell that there should be extra attention to dehumidification and ventilation in this project, because almost all the diagram is, red. And that should, take some energy. Other helpful observations can be made by looking at each of these diagrams and figures here, which will really help with maximizing the use of passive design strategies and reducing the use of active systems and EUI in your building. After learning more about the climate, we started with massing studies, coming up with different forms. With drawing tool, I could quickly mock up different massing options and run it through energy and daylight analysis tools to assess the performance of each alternative, or like each option. Here are 4 options from simple to more complicated geometry that I mocked up in drawing tool. The options can be totally different from each other and not necessarily like this. They're kind of similar. We had some limitations in the project, so we could not really come up with very different forms. So the form was, specified prior to coming to us, sustainability as sustainability consultants. Once you have your geometry in the tool, either by drawing it in the drawing tool or importing your geometry to cove.tool with plugins, you can run daylight and glare analysis to see how much daylight the indoor spaces receive, and also the glare risk. The carve-outs from the initial geometry in this project really help with improving the SDA and ASE points to increase daylight availability inside and reduce the glare condition. So SDA and ASE are 2 famous metrics, daylighting metrics. SDA stands for spatial daylight autonomy. It's a percentage that represents the percentage of spaces within your floor plan that receive enough daylight throughout the year. And ASE stands for annual solar exposure. In simple words, it represents glare. It's a percentage that represents the percentage of spaces within your floor plate that receive too much direct sunlight, like more than 1,000 lux. Also, we took a look at, we talked about the importance of views on students' health and productivity earlier. It's interesting to mention that the study finds that spaces with high view excess have about 6% premium over those with low view access. So this can also be a financial incentive for developers to optimize for both view and daylight. cove.tool provides 4 types of views analysis based on lead criteria, including total quality view, 90-degree sidelines, sky and context, and obstructed views. We just ran all these analysis and improved the geometry to get good scores for each of the view analysis. For the energy and operational carbon part, I first set a target with the design team based on the baseline and the benchmarking table with high and low EUI range. So again, the first time you open the baseline energy page in cove.tool, you get all the code minimum inputs populated in the page, and you will see a baseline EUI, energy use intensity, based on all those code minimum inputs. So even if you're in the early design phase, if you're in the schematic or pre-design phase, and you don't have enough details or information about your project, you will still have a number to start with. And you can actually use that number for benchmarking and setting target for your projects. For this project, we decided to hit the 2030 target with an EUI of around 21. So you can see that in the section that I marked with blue. This high and low EUI ranges are based on my project size, its location and typology, and the values are calculated based on CBEX data. In the next step, I made adjustments for reducing the energy consumption to match the target EUI. So my baseline EUI with code minimum inputs was 36. A good efficient building will have an EUI of 21, and the national average for a building with this typology, size, and location is 108. So based on these three numbers, like a EUI, which represents a EUI for a low performance design, an EUI, which represents a building with a high performance, and the baseline, I was able to just set the target for the project. So my first step to reduce the operational energy was to increase the insulation of the building envelopes. I increased the wall and roof R value and reduced the window U value since the code minimum requirements were pretty inefficient. So this is because the state of Georgia, this project is located in Atlanta, Georgia. The state of Georgia still complies with ASHRAE 2013. I mean, projects in the state of Georgia should still comply with ASHRAE 2013, which is ICC 2015 equivalent. So this is an old version, and the values have not been updated, so they are not really efficient. Considering the current standards. But yeah, these three changes, plus changing the envelope heat capacity from light to medium due to the use of brick as the main material in this building, reduced the EUI by about 2 points. So the EUI was about 36, and now with changing these inputs, it is 34.66. Next, I made several changes to the occupancy and schedules tab, the second tab here in the baseline energy page. I entered the exact number of occupants, which is 400. This number was initially set to 800. So the total number of occupants is calculated based on the building area and also the occupants density. And the tool calculated this as 800, but based on the information we got from clients, only 400 people would occupy this building, so I changed that. I also adjusted the occupancy schedule based on the operational plan according to the project owner. The classes start from 8 and ends at 3, and the school is closed during the summer. So I just made the adjustments so you can see that the occupancy schedule, my proposed occupancy schedule is actually different from the default schedule. Then I reduced the lighting power density and changed the daylight and occupancy sensors field due to the use of efficient LED systems and full sensors for 100% of occupied and unoccupied spaces. And I think these were all the things that I changed. These changes, however, significantly reduced the EUI from 34 to 26, which is almost 8 points drop. The main drive of this significant reduction was changes to the occupancy schedules in a way that systems need to run fully for less hours, and also a reduction in lighting load due to the use of more efficient systems and sensors. Next was the HVAC selection and changes. So one should keep in mind that a school's biggest expense after payroll is its utility bill. Because the HVAC system is a major component of a school's utility bill, careful evaluation of a school's HVAC requirement and equipment options can help administrators save money while actually improving learning productivity and indoor air quality. So every school is different. So there's no one HVAC solution for all the schools. Instead, there is a best solution for each individual school, uh, chosen from careful evaluation that maintains the highest possible indoor air quality at the lowest possible energy cost. So when it comes to HVAC system selection, you definitely need to closely work with your mechanical engineers to come up with the right solution. For this project, we considered 3 HVAC options, including a single zone equipment with electric resistance and package DX, a dual system with gas boiler and air-cooled chiller, and a VAV system with gas boiler and water-cooled chiller. A single zone system is considered a simple, rather cheap option that is used in many schools. It's kind of typical, especially for elementary schools. DOAS is selected due to its dedicated ventilation system, which provides high quality indoor air and comes in handy in situations like COVID pandemic situations. And VAV is selected due to its cost effectiveness. So here you can see the results for 3 options. DOAS reduced the EUI the most, while single zone reduced the EUI the least. Due to the project emphasis on indoor air quality, ventilation, humidity, and energy efficiency, we decided to continue with DOAS system with a gas boiler and air-cooled chiller. And you can see that with the use of DOAS, we were able to reduce the EUI from 26 to 24, so 2 points drop. And in the last step, to reduce the EUI, I added some solar panels to the project. Here, I entered an estimated solar panel area that is financially feasible for the project, along with some other basic information to calculate the amount of energy offset. So we came up with this surface area with careful considerations with the project owner and other consultants in the project. Solar PV or solar hot water systems can be simple add-on renewable energy features to include in building designs. More and more of our K-12 projects are considering photovoltaics today. Honestly, many times these systems are added for the purpose of creating a media snippet, but they provide an excellent opportunity to reduce fossil fuel use for a facility. So design teams should always look for opportunities to include renewable energy systems to achieve an owner's design for long-term energy saving and reduce impact on the environment. Here you can see that with 10,000 square feet a school panel surface with 35-degree angle and moderately ventilated, we can offset 11 points from the total project EUI and reduce the EUI from 24 to 13. Note that solar radiation and sun hours analysis on the 3D analysis feature can help with deciding on the location of the PV panels and slightly with their production capacity, because they show the radiation intensity and also radiation hours on each surface of your geometry. So you can take a look at these analysis on the 3D analysis as well when it comes to PV design. So you can see that changes we made to the project resulted in about 23 points drop in EUI, 14 more estimated lead points for optimized energy category, about $44,000 operational cost saving, and also getting below the benchmarking target that we set early on in the project. So our goal was to hit the 2030 target, which was EUI of 21. But adding renewables help it going, further below our target. We also calculated the operational carbon emission by multiplying the location-based carbon factors by energy consumption. So that's the way we calculate the carbon emission operational. In this case, you won't see a significant carbon emission reduction because of no energy change to the gas sources. Although the primary heating energy is electric, but the primary energy for domestic hot water is gas. and we didn't really change any gas-related inputs on the baseline page. So although the EUI change is significant, you won't see a significant reduction in the actual emission of your project. So, oops, sorry about that. Um, The next is the water efficiency. So actually, we did not run a water use analysis for like water calculation analysis for this project, but I wanted to have this slide and give some general tips. General tip is that plumbing designs should be geared toward water conservation and the use of recycled water or reclaimed water for toilets and urinals. Also, use of water efficient fixtures help with saving energy. The only consideration is that when using low flow plumbing fixtures, ensure they actually pass the solid paper waste appropriately, because previously in some school systems, due to the type of toilet paper, um, which were used as a standard, it takes multiple flushes of low flow plumbing fixtures to pass the waste. So water saving is not normally achieved in these situations in this particular case. So there should be some consideration when it comes to installing a low flow plumbing fixtures in the school. And yeah, I mean, this was part of what we did to assist the design team in this project. The rest doesn't really fit into a 30-minute session. This was a pretty short session. To wrap up the presentation, we should really understand that a good school design should first focus on students and teachers' health, and then focus on the environment by reducing the carbon footprint, and also operational cost is a bonus to this, consideration and good design. As a result of all this consideration, we can achieve higher test scores, higher attendance rate, higher teacher retention, significant cost savings, and also protection for the environment. Thank you for your attention. We are right on time. We have about 1 minute, but I can actually stay. I don't have like a hard stop. I can stay on the call in case you have questions.
Zara, there are a couple of questions in the Q&A section.
Mm-hmm.
So the first one is, the Georgia school example only seemed to evaluate gas boilers as a part of the HVAC system. Was an all-electric solution ever evaluated?
Unfortunately, that was not an option. Like in this project, we were not to use 100% electricity. So yeah, all the options, all the HVAC options actually had a gas boiler with them.
Yeah, and then
Mhm.
the other one is, what about looking at a DOAS system with indoor VRF pumps?
Yeah, I mean, VRF is also a very cost-effective option. A lot of the schools use VRF combined with DOAS. But again, we decided to, based on like our conversations with the mechanical engineers, with the MEP team, we decided to just assess these three options. But yeah, definitely VRF, it's like a good choice for school design, for school building type, but it was not part of our options. Is
Yeah,
there
looks like that's it. Those are all the
okay?
questions.
Any other question? Okay. I'm not seeing any other question in the QA or chat. I think with that, we can just end the call. Thank you again for joining this session, and hope you all have a great rest of the day.